Hi everybody, I'm going to go over a little bit about induction and bond types in this video. By bond types, we're really talking about the ones that you learned in Gen Chem in terms of covalent, polar covalent, and ionic. Okay, so and we're gonna that's gonna help us try to determine where we have reactive places on molecules in organic chemistry. So first off, for induction, in case you don't remember, this is the definition. So it's the withdrawal of electron density that occurs in a bond between two atoms of differing electronegativities. So it's that idea that if you've got, something really electronegative bonded to something semi-electronegative, they're not necessarily sharing that electron density in the bond between them exactly evenly, right? They are not sharing that equally. You're going to have the more electronegative atom is going to be holding more of that electron density closer, and then taking more away from the other atom that's involved in the bond. So the way that we go about showing that is we show it with these partial positive and partial negative little notations. So this is just delta plus, delta minus. So the delta plus is the partial positive charge. Okay, and that's what would go onto the less electronegative element. And then the partial negative charge would be the one going on the more electronegative element. Okay, so they are different from the formal charge that we've been using so far, where we've been doing, this or that. It is not those. Those mean like there is a full positive charge on this atom in this molecule. But these ones, they're just partial, so they're not as strong of a charge as like just a straight up positive or negative. They're just kind of a semi-charge, and that's what happens from induction. It's not making anything full. We're just making kind of partial charges along the way. Okay, so it's important to think about induction along with bond type. And I have the little table electronegativity over here because we're going to need it for some of the stuff that we're going to be doing. So covalent, you're really looking at an electronegativity difference that is less than 0.5. So if you take, a bond between carbon and nitrogen, you're kind of right on that covalent border, right? Because you've got 3 minus 2.5 is 0.5. So that's going to be starting to get out of the covalent. But if you look at something like carbon and hydrogen, that is a difference of 0.4 on that scale. So we can see that carbon-carbon bonds, carbon-hydrogen bonds, those are all really good examples of just covalent bonding. So the next one is polar covalent. That's going to be looking at electronegativity differences between 0.5 and 1.7. Okay, so if I've got something, as we said, kind of the carbon nitrogen is right on that cusp. So it technically falls into the polar covalent because it's not less than 0.5, it is 0.5. When we've got things like carbon bonded to oxygen, that's going to be polar covalent. Oxygen to hydrogen is polar covalent, hydrogen to nitrogen, and so on. Okay, so it actually covers a whole lot of different bonding options. We can go ahead and add OH on here. All kinds of things are going to end up being a polar covalent. Most carbon, so carbon with fluorine would be, carbon with chlorine would be, carbon with bromine is not, which is interesting, but still has a little bit of difference in there. So that's the polar covalent. So that's ones where we're certainly not sharing that electron density evenly. In the case of the more electronegative atom, that's the one that's going to be holding it. So if we were going to use our partial positive, partial negative charges here, partial negative charge is going to go on that most electronegative atom. So over here, it's going to be nitrogen. And then the hydrogen is going to be partial positive. Carbon is going to be partial positive against the partial negative oxygen. Lithium is over here. So that's actually a polar covalent bond with carbon. In that case, carbon is the electronegative atom and lithium is the positive, and then delta minus, delta plus for the H, okay? So that's kind of how we're going to use that notation, and it's going to help us visually see, you know, where is our electron density kind of tending to lie, right? It's going to go towards that electronegative element or atoms. Okay, so ionic bonds, those are anything with an electronegativity difference greater than 1.7. So that's going to be things like sodium chloride would be one of those, right? Sodium hydroxide, I think. Let me calculate that real quick. Yes. Right, so mostly when we're looking for ionic, we're looking for stuff that happens, that shows up on the left-hand side of the periodic table, bonding with stuff on the far right. So any of those kind of salt type of things are going to fall under that ionic category. And remember, back in Gen Chem, we didn't even draw them with a line. These are typically drawn as, oops. Right, the ions, where we're just showing, yeah, we've got two ions that are kind of hanging out next to each other, but they're not really bonded. Okay, so something like that. So that's, you don't actually even draw a bond for those. Okay, so let's look at a couple of examples here, just so that we can do a little bit of identifying those polar covalent bonds. Those are going to be the ones that we work with the most in organic chemistry. Covalent bonds tend to not want to do a whole lot. And ionic bonds, they do a lot, but it is a little bit harder to make them with organic molecules, because it's just hard to get, you know, something like a carbon to have that big of an electronegativity difference. Okay, so let's go ahead and start with the top left molecule here. So this is actually butyl lithium, and we're gonna learn nomenclature soon, but butyl means 4. So this is 1, 2, 3, 4 lithium, okay? So that's where the nomenclature comes from. Again, we'll talk about that. So all of these bonds here are all covalent bonds, right? It's just carbon, 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 hydrogen. There is absolutely nothing special about them. But here we have quite a severe difference in electronegativity, right? So we've got lithium, which shows up at 1, and carbon is 2.5. So this has a difference of about 1.5. So that falls like pretty close to the ionic range of the polar covalent territory. So this one is going to be delta minus to lithium's delta plus, right? Because we're always going to have the more electronegative atom hold most of that electron density, and then the least electronegative holds the least amount. All right, so let's take a look at this one. This is something you'll become very familiar with if you go into Organic 2. This is called a Grignard reagent. They're really good at making carbon-carbon bonds, which is a special thing. It doesn't seem special, but it is. So here, again, all of this stuff is just covalent bonding. So we're really looking at this match, because the magnesium falls on the left side, carbon falls more towards the right side of the periodic table. So over here, we've got carbon is more electronegative, magnesium is less. And then if we were going to compare magnesium and bromine over here, right, the bromine is definitely minus. And if we look at our differences, 1.2 to 2.8, so we're still squarely into that polar covalent region, right? And this is just telling us that we've got a more electron dense area here, or more electron rich, however you like to say it, in both of these locations. So we have something where we can have essentially use that electron density and then go and form a bond with something else. And that's essentially what these two things do, is that's how they act. They go make bonds with other positively charged things. Okay, so let's go ahead and look at the next one. So we're going to look at, this is called formaldehyde. It is an aldehyde type molecule, and we will learn functional groups soon. So in this case, we've got oxygen, we've got carbon. Oxygen is the more electronegative of the two. That's going to be our delta minus. Carbon is going to be our delta plus. This is something we're going to see this pattern over and over and over again. You're probably going to get exhausted by this pattern, but we're looking at oxygen being 3.5, carbon being 2.5. So we're nicely snug in that polar covalent category. Okay, so let's go ahead and look at this one. Again, this side has that same kind of covalent nature, carbon, hydrogen, not big differences. But as soon as we start looking over here, anything that's really attached to the oxygen, that oxygen is going to be delta minus, carbon is delta plus, and the hydrogen is also delta plus. Okay, so this is the most electronegative, and these two are less electronegative. And again, these are more polar covalent. Alrighty, so then let's look at the last one here. Again, we can pretty much just discount all of the carbon-hydrogen bonds, but we do have a carbon-bromine bond. So in this case, the bromine is actually not that electronegative. And in comparison to carbon's 2.5, bromine's 2.8, it actually falls into covalent category, into the covalent territory as well. So let's look at one different option here. And we'll just change that bromine to chlorine. Okay, so once it's chlorine, if we look at 3 to 2.5, now we're starting to verge into that polar covalent territory. It would be even more polar covalent if I picked the fluorine option here. Okay, but we'll just stick with the chlorine and we'll go delta minus, delta plus. Okay, so that's kind of how we're going to start looking at these bonds, and it's going to help give us a bit of an idea in terms of, you know, finding dipoles, thinking about intermolecular forces, and just thinking in general, where is the electron density sitting in these molecules. So as always, let me know if you have any questions, and I will see you all later.